All right, hi everyone. Welcome to our lightning talk on a few myths about open source security that developers believe, including myself and Jess not too long ago. I'm Tim, by the way. I'm a software engineer, and I mostly work in the space of open source dependency analysis.
And I'm Jess, and I work on vulnerability management inside Ghost.
Okay, myth number one, Git tags are immutable. So on the surface, it's true. Like if it's like a read-only variable or a constant, in that if you were to create a git tag foo, for instance, to point to a commit abc1234, you can't reassign it afterwards. Except, no, you can do this. There's no magic here. Like, you really can just drop a tag and recreate it with the same name and then force push it upstream. It feels a bit trivial to stand here and point out that you can do this, but the fact that you can does have some very interesting / dire consequences to open source supply chain security. Yeah, let's look at Go, for instance. In Go, we use checksums to make sure that you don't get packages that have been tampered with. I think that's pretty sensible. And also, Go has a policy where you can only upload a version one time. Afterwards, you cannot modify that version again. And I think that's also pretty sensible. Okay, putting on your black hats, you have a malicious package, foo version 1.0.0, that you want people to consume and run. What do? Unfortunately, here's what you can't do. You can't just upload a good version first, shift the tag to point to the bad version, and expect Go is going to publish this. Nice try, but checksums would catch you here. This is the whole point of having them. So you can't do that, but what you can do is you can upload a malicious version the first time. Go is happy for you to do this because it's the first upload. And then you can move the version tag v1.0.0 from the bad version to the good version. And the clever thing here is that, well, you move the v1.0.0 tag from bad to good, but in fact, Go is still happily distributing the malicious version you published the first time. And this is great because, well, you can shake off suspicion very easily. Like, anyone who suspects foul play in your project here, they can inspect your source at version 1.0.0, and they'll find absolutely nothing wrong. Unfortunately, this sort of thing is not a toy example, because in 2021, someone actually uploaded a malicious version of the BoltDB project under a very similar name. And we call this sort of thing typo squatting, by the way. And in this instance, they pulled off the exact same trick that we just went through in the last minute or so. It really was that easy, and they had remote code execution on countless projects. And what surprises me is they had a good 3 years before people actually picked up on this. In case you're curious, tag rewriting, it is a fairly rare occurrence, but it certainly happens, and people do abuse it. In that example, that was 1 out of 8,084 instances. I think we should all be asking whether the other 8,083 are innocent. So please remember, you really can't reassign a git tag after creation, but you can just drop and recreate it, which is functionally the same thing. Myth number 2, there is only one dependency graph. Suppose you're working on a Node.js project, you hit npm install express. When I did this a few weeks ago, you happen to get 5.0.0. This notation with the caret, by the way, just means your project is happy to accept anything 5.0.0 onwards, but just not up to 6. And as of right now, there happens to be around 3 valid versions that can satisfy the versioning constraint. So here's our situation. Your project depends on Express. There are 3 valid versions to pick from. This is not so complicated, but Express has its own dependencies, one of which is body parser, for instance. And as of right now, there happen to be around 5 versions for that. And really, I'm just showing you a very small snapshot of the overall dependency tree here. If you've worked on a Node.js project, you know that there are many, many more layers in reality and many, many more dependencies each layer. And very quickly, it stops being a dependency tree because, well, packages can start having 2 or more dependents. And the crucial thing is, if you were to run npm install again, say a month later, or even on a different machine, it's entirely reasonable that this graph is just thrown into complete chaos, and a wildly different one might emerge. And it really is the case that just depending on the time of day or time of year, the package manager you're using, even the precise version of the package manager you're using, your operating system, your machine's architecture, just all these small inputs which constantly fluctuate between person to person, time to time, machine to machine. All these small inputs really might just cause an entirely different dependency graph to emerge. Here's the package D3 at random version 7.8.5, for instance. What you're looking at here is all of D3's direct and transitive dependencies. Relative to other packages, this is actually quite a modest dependency graph, but you would actually have 10 to the 81 distinct valid dependency graphs, like roughly. And that's more atoms than we have in the observable universe. So this really, the significance of all this is to know that every single one of those 10 to the 81 valid dependency graphs can represent potentially an entirely distinct attack surface, of course, a different set of vulnerabilities, and in some cases, you might even get wildly different application behavior. So in summary, there's never the dependency graph. There's only ever a dependency graph at this specific point in time on your particular machine, using this specific package manager at this specific version, and so on. Okay, myth 3.
All right, so here's the myth that names are unique, which is simply not true, not across ecosystems, not across registries or namespaces, and even when you ignore typo squatting or homoglyph attacks. For example, if you have a GitHub repository for a package named bar, which probably exists, and you haven't claimed it on npm, a malicious actor can come along and say, hey, that's a popular package that hasn't been registered on npm. Let me just snipe that name from npm and instead give it a version 100.0.0 and hope that some developer might come along and then run npm install bar instead of downloading the right repository. And then they might inject some malicious code in the build script, and yay, now they have remote code execution again. That was a quick one, but I'm going to get into myth 4, which is fun. So CVEs are unique and have no data quality issues. Let's start with the first part. Nope, this has 8 CVE aliases that are all complaining about memory safety in the same project. They were discovered during an audit, and while the CVE submission format allows for all of these duplicates, I'm not sure what the point is. Unless you have proper reachability analysis tooling incorporated in the scanner, this information is essentially not useful for the end user. It's kind of just generating extra churn and makes more noise for developers who want to keep their projects safe and vulnerability free. And then the second part, no data quality issues. I'm not sure anyone actually believes this, but we'll go through a couple of interesting entries anyway. This is a CVE I found. It seems to have a solid amount of information. It mentions a project and the plugin. And it seems to have the version isn't known, and there's some links here, but they just say that they aren't affected. And then when you do look at the actual GitHub repository, that hasn't had commits since 2020, which could just mean that it was never fixed, or it might be an internal version, but then publicly this isn't really useful. But then, yeah, so I'm not sure why this is useful to a user. Here's a different one. It has no vendor, no product, and no version. It does have some reference to a project and even a commit hash. And oh, look at that, we are also supplied a GitHub link, but it goes to the markdown file of a research project, which actually also links to the actual GitHub inversion, which I don't know why this couldn't have been provided in the original CVE. Yeah, so a little bit of insight here to our future work. We are looking how we can utilize the web, some AI, and turn these sorts of CVE records into much better quality output in the OSV format. And then this one is fun. When was this published? Say it with me. Yeah, 2025. Which is because of the numbering system, the CNA probably ran out of pre-allocated slots. But yeah, in general, when it comes to CVEs, we just can't assume anything. And why is this so bad? It's mostly just the juxtaposition of stakeholders across the CVE program between the finder, the CNA publishing the vulnerability subject owner, and the vulnerability impacted user. Everyone has different priorities of outcomes. And our final myth everyone's been waiting for is the myth that you know your code. You may have written it, you may have reviewed it, and sure, you might know what your code does on a high level, but after all we just talked about, are you really going to tell me that you know your code, that you know what your dependencies call, what their dependencies call, that you aren't being maliciously typo squatted, name squatted out there, that like, if you know your code, why is there so many vulnerabilities each year? Even the simplest projects can hide so much hidden complexity. So yeah, thanks for listening. Feel free to check out our projects for more information on the work we do. And if you're interested in going deeper in any of these topics, I've attached some resources to some parts of this.